Welcome to Pomodoro Joe for Monday, August 7th, 2023. Today we're looking at LeetCode problem 74. Search a 2D matrix. This is a medium problem. You are given an m by n integer matrix with the following two properties. Each row is sorted in non-decreasing order. All right, so they're increasing. And the first integer of each row is greater than the last integer of the previous row. All right, so that means this integer will be smaller than this one. Okay. Given an integer target, return true if the target is in the matrix, or false otherwise. You must write a solution in O log of m by n time complexity. All right, so this is a binary search problem. So the fact that it's telling me I have to solve this in a log of some value, in this case it's m by n, that means that we have to do this as a binary type search. We'll have to take our entire search space and divide it in two, basically halve the search space every step along the way. That will give us a log m by n runtime solution. All right, so how do I have a 2D matrix? Well, I could have it going this way. I can do a vertical split, then I have a left and a right, or I could do a horizontal split and I have an up and a down, or a top and a bottom. But oh man, thinking about trying to split this and then split it again and then split it again, it can be done, don't get me wrong, but to me it kind of hurts my brain. It's a little bit too much. So one thing I do know is this tells me basically every row is increasing and the first element of the next row is always greater than the last element of the previous row. So I could treat this as just one long array of sorted values that happens to be arranged in a matrix. So it would go from left to right and then wrap around and go left to right again and wrap and left to right. So mentally I can just stitch these all together so it just makes one long array. This is the first element, this is the last element. So I think that's what I'll do. I'll just treat this mentally as one long array. I can't actually make it one long array because that would be an O of n operation just to do that one step. So I can't actually convert this to one array, but I can mentally think about it this way. All right, so with that, we'll put 25 minutes on the Pomodoro timer and we will get started. Okay, so if I'm mentally thinking about this as one long array, that means I have one index into my array. I don't have a row and a column, I have a single index. This is index 0, and this is index m times n. Okay, so first let me get my dimensions. Let's do that, because I know I'm going to need these, so I'll have some row count. And that will be the length of my matrix. Okay, so the length of the matrix, that's how many rows there are. 1, 2, 3 in this case. All right, and then I got my column count. And that's the length of the matrix at index 0. So this is the first row, the 0th row, and this will tell me how many elements are in that row. That's how many columns I have. Okay, I got my row count, my column count. Now let's define some conversion between an index and a row and column. So because I'm treating this like one long array, I'll need an index that converts to a row and column that I can actually go and grab that value out of the matrix. So I'll have an, let's see, index to coordinate. All right, and this will take an index. And this will return a row and a column. So what's my row? Well, let's see. Maybe I'll do column first. That's a little bit easier. For now, I'll just say this is none. I'm just gonna, these are temporary, don't worry, we'll go back and fix that. And then I will return a row and a column. Okay, so once we have this function in place, we can take an index and we can get a coordinate out. All right, so now this just becomes a binary search. Pretty straightforward binary search. If you haven't done binary search before, I'll try to leave a link in the description. All right, so this becomes a pretty straightforward binary search. So for this, we'll have a search matrix recurse. I'm going to do this recursively, but you can also do this iteratively. And this will take, let's see, I need to have a low and a high, or a left and a right. I'm going to go with low and high. So So this will have a low, and that's an index. Maybe I'll call it low index and high index. Okay, so this will confine my search. So initially I'll have low as 0 and high as the max value. That's the entire search area. Each step along the way, I'll either be raising my low index or lowering my high index to cut my search area in half. And at some point, I'll reach a base case. Now in that case, if the low index, if this is greater than my high index, now I've reached the end. I can't split this anymore. I've actually crossed my indices. So at this point, we're done and we haven't found our value. So I'll just return false. All right, next we'll find our mid index. If we haven't reached the end, we have some midpoint. We need to find what's the midpoint between my low index and my high index. So that's the mid index. And for this, again, this is pretty straightforward. The more you do this, you'll just naturally know how to do this. But I'll need to essentially take my entire search area. So that's my high index minus my low index. So this tells me how many different values I have in my search area. And then I need to divide that by 2. That's an integer divide by 2. So this will split how many elements I have to search in half. But it doesn't give me the actual indices until I add the low index back in. So this gives me my base where I start from. Then I take the number of elements from my base in half, and that's my midpoint. Okay, so now we found our mid index. We have to convert that index into a coordinate so we can get the value at that index. So let's do this. Chord. I've got my function up here, index to chord. We'll pass in this mid index. All right, now let's get the value there. So I'll just call that value. So that's going to be my matrix. And we'll do row first. And so that's the coordinate at index 0. And then we'll do the column. So that's coordinate at index 1. Okay, so this is the value at this spot in my index. So that converted my mid index to a coordinate, and then I grab that value out of the matrix. Now, if that's the value we're looking for, so if the value is equal to the target, then we're done and we can return true. Okay, if it's not the target, then this value is either greater than or lower than our target. So let's check. If this value is less than our target, that means that we have to search higher in our matrix or higher in our sort of virtual array that we've created. So this value is lower than our target, so the target must be higher than this value. So we can raise our low index up. So the low index will now be equal to the mid index. And we can even go +1 because we know it's not at the mid index, we just checked. So we've raised our entire search area up from the low index, now starting at the mid index, to the high index. Otherwise, we know that this midpoint is actually greater than the target that we're looking for. So the target must be lower than this mid index. So our high index will become the mid index. Now, in this case, I don't subtract 1. This has to do with the rounding of this integer divide. So you just want to lower this down to the mid index. You don't want to go further than that. So this low and this high index, these are going to be the indices that will pass into a recursive call. So we'll just do another search on these new indices. So at this point, we want to return. And it'll be the search matrix recurse with this new low index and the existing high index. And same thing down here. We'll do a recursive call on this existing low index and the new high index. Now, I don't actually need these helper variables here. Instead of doing this, let's just take this and add it directly. So our low index becomes mid index +1. We'll do that. And our high index just becomes the mid index. All right. And that's it in terms of our recursive function. Now, we still have a couple things we have to do. We haven't really implemented this index to core, and we haven't kicked off the initial search. So let's do that out here. So initially, we do have to start the whole thing off, and we'll just do return search matrix recurse. And in this case, we have a low index of 0 and a high index of basically row count times column count. All right, so this will initially start with the entire search area, and then every step along the way, it's going to cut that area in half by using this mid index. And then at the end, we'll return whether or not it's got this value. Okay, let's back up, go to our function here. Index to coordinate. Okay, we've got a row. How do we know what row we're in? Well, the row has, in this case, 1, 2, 3, 4 values in it. And then there are 3 rows. So if we have an index, let's say index 0, how do we know what index we're in? Well, every row has 4 values in it, or column count number of values in it. So if we divide our index by our column count, and we'll do an integer divide. So let's see, that should give us our row. So if we're 0, 1, 2, or 3 divided by column count, which in this case is 4, 0 divided by 4, 1, 2, 3 divided by 4, integer divided by 4 gives us 0, which is column 0. As soon as we get to 4, that's this one out here, is index 0, 1, 2, 3, 4. Index 4 divided by column count 4 gives us 1, and that's indeed row 1. So our row will be our index, integer divided by our column count. Now what about the column? Well, that's very similar. That's going to be our index, but we're going to do a modulo column count. So the modulo will give us the remainder. So if we're dividing 1, or in this case 0, 0 divided by 4 is 0, and now our column count, 0 modulo 4 is still 0, so this is 0, 0. All right, what about index 2? Or that's index 1. Yeah, let's go to index 2. So index 2. 2 divided by 4, integer divided by 4 will round down to 0, so that's row 0. Now 2 modulo 4 will give us 2, so that's indeed 0, 1, 2. So this will give us the right thing. What if we jump to some other value? Or let's do 5. All right, this 11 is in spot 5, so that's 0, 1, 2, 3, 4, 5. That's our virtual array 5. All right, so 5 divided by 4, you get 1 for the integer divide, so that's row 1. And then 5 modulo 4, well, what's the remainder when we divide 5 by 4? You have 1, so it'd be 1 with the remainder of 1, and this is indeed index 1 in our column index. All right, so I think we've got our index to coordinate conversion. All right, so this is the last piece. And it looks like I need to change this matrix. There we go. All right, so we have our row count, column count. We're going to use that column count here when we do the index to coordinate conversion. Then we have our binary search. This is pretty standard binary search. And then we have our initial call. All right, let's give it a shot. Oh, looks like I've got a bounds issue. In that case, I got this slightly wrong. If the low index is greater than or equal to the high index. I should have caught that. Let's try this again. You probably saw that. There we go. All right, let's submit this and see how we do. And we pass. And how do we do? We do pretty well, actually. We beat 80% for runtime and 64% for memory. So yeah, that's not bad at all. Okay, so we could jump back here and do some cleanup if we want. Like, we don't need a separate function for this. We could actually move that whole thing into here. It was just easier to break it out into a separate function. We could use our helper variables. Sometimes that helps. Might give us a little bit of a boost. Might not make any difference at all. We could try using caching, but we really shouldn't be calling the same function more than once with the same inputs. So that's probably not going to make any difference. We could try shortening these variable names. There's one thing we could try here. So this is basically the same as this. All right, we can try that. That saves us a little bit. I'll collapse that a little bit. All right, let's try this. All right, that gives us a little bit of a boost. Now we're at 90% with 28% for memory. So yeah, that does give us a little boost. 90% for runtime, 28% for memory. And that's just a little trick. To me, it's more intuitive to go the other way, the low plus the delta between the high and low divided by 2. But you could just do high plus low divided by 2. All right. Well, I think that's about it for me. We're at a 90%. I'm pretty happy with that. So that's how we do this one. All right. For this one, we kind of make a mental leap where we turn this 2D matrix into a one-dimensional array that just goes from 0 to m by n. And we can divide that search area in half every time by using an index that will grab the midpoint from every step along the way. That should give us a log m by n runtime. All right. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.